Hello everyone, my name is Abhinav Mukherjee and today I'm going to present our new work from Clutter to Clarity, Visual Recognition through Foveated Object Centric Learning or FocL. My co-authors are Deepak Ravikumar and Dr. Kaushik Roy and we are from Purdue University. Let's look at the problem here. Here on this graph we show the effective sample count on the y-axis and the sorted sample index from on the x-axis, which shows samples from easiest to hardest, which is measured by a proxy say. And as seen from the graph, what we see is that easy samples occur towards the mode, and as we approach the tail, harder samples come. Now, what makes these samples really difficult to learn? So there might be spurious co-occurring features between in the image that kind of causes semantic contamination of the label, such as in all of these classes, human features are present, which is not even a class in the ImageNet dataset. Or you can have multiple classes or multiple objects in an image where the label is only one. And a primary reason of these kind of shortcut learning is that you learn the image in one shot. That means you do not have the right foreground to label alignment because you just take the image, you take the label and just learn it one shot for image classification. But in order to tackle this problem of shortcut learning, which can lead to overfitting and in the worst case memorization, can we do something different that tackles this problem head on? So let's see, to tackle the problem of shortcut learning, can we do something slightly in a different way? And to do that, let's step back and look at active vision, the way humans or animals learn in the real world. So visual information in human brains occur via two separate pathways. The dorsal stream, which is responsible for locating the object or is responsible for spatial awareness, and the ventral stream, which is responsible for classifying or understanding the object once the dorsal stream has localized the target. Now, this is how information or visual information is processed in the brain. Now, in order to extract the right information from the environment, you have the human eye, which has their own mechanisms like saccadic points, which helps in scanning the environment based on where we're looking. And also, once we know where we're looking, we kind of only foveate on those regions and the rest is blurred. So these four are important components that make an active vision system. So now, different than a passive AI system which takes image and learns one shot, here we have the right mechanisms in order to first look at task relevant features, and then once we locate the task relevant features, actually understand what are the salient properties through mechanisms of foveation. And we learn the salient features, through our ventral network. Now, if we want to map it to a deep learning setting, the dorsal network are localizers. It can be detectors, it can be regional proposal networks, or it also can be a foundation model like SAM, which gives you the spatial locations of different objects in a scene. The ventral stream, on the other hand, are our classifiers. It can be CNNs, it can be VITs, or it can also be attribute classification networks, depending on what exactly we're learning, what properties we're interested in given we know where the object is at. Saccades can be 2D points, which gives you the midpoints of different bounding boxes. We can learn saccades, or also we can start with random saccades in an image and try to see which points are important for our task and which points are not. Now, foveation is the mechanism through which we actually learn the properties of the object at hand. So these are crops centered around a 2D fixation point. In general, foveation can be modeled as a peripheral blur, like in literature we have seen. Also, we can look at as something like foveation with hard cutoff. That means extreme cutoff. That means we just crop the image and the rest are set to 0. In this work, we are going to focus on this kind of foveation, and the network we're looking to train is a ventral network. So let us actually see the benefits of foveated vision. So given the image or set of images we saw in one of the previous slides, what happens is that once we foveate on the right foreground, then we actually look at the right information given the task in hand, which is, say, classification. And this preserves intra-class consistency. That means different samples with the right foreground preserves the features that are responsible, the key features that are responsible for their classification. The other is it reduces interference from co-occurring features. Like once we foveate on the cap or foveate on the fish, we can remove the background human here, which also benefits learning. The other is it preserves the right object label consistency. Now from this one image which has three distinct objects but one label, you can actually perform foveation, crop it out, and then you have the right label and image for this setting. Also, you can get more samples if you have access to those labels as well. So these are some of the benefits of foveated vision. And now next we propose our FocL algorithm to train vector classifiers through this foveated object-centric learning methods. Introduce our FocL algorithm, but before we do that, one key point. For our training, we use samples with annotated bounding boxes. Now the goal of this work is not just to introduce the FocL algorithm, but also to show the benefits of such training. So in order to do that, we choose annotated bounding boxes since they give you the precise supervision of the foreground by removing the background. Now, we could also use a foundational model like SAM or any other proposal network to generate pseudo-bounding boxes. But again, any network proposed boxes is probabilistic and might incur some sort of error, which we want to avoid because reiterating the fact our goal is to show that the downstream tasks are benefited by this algorithm. Now let's see. So we take this image, it is cropped with the help of the given bounding box, and the red point P here is, say, the saccadic fixation point that we mentioned earlier. So our X is now the foveated crop given the actual image and the saccadic fixation point P. So step one will be to generate parafoveal fixation points around P given slightly jittered actions. So these are like deterministic jittered points that are generated given the actual image size and the bounding boxes. And the details are mentioned in the appendix of the paper. So once you generate these fixation points, then you have a parameter, a hyperparameter that you choose depending on how many fixation points that you want to sample from here. Here in this image, we are showing 3. In the paper, we do 1 and 3, but you can choose more depending on the data set and your application region. So if we choose this fixation points, these 3 different blue points, then what we do, we crop these glimpses around these blue fixation points, and these becomes the 3 different glimpses on which we're going to train the model. And then the final is that the data augmentation that is applied in an image recognition pipeline is applied on top of these glimpses. And here now, after this augmentation, we just train our classification model to predict the classes. Now, this gives the FocL training equation. One key point is the K is given over the 3 different glimpses. So K is 3 over here. And another key point is that during our training, we do not shuffle across these glimpses. The glimpses are contiguous in our training set. So again, the samples are shuffled following a standard training pipeline, but the glimpses are not shuffled just to show or provide that inductive bias that these glimpses come from the same sample, and these are just jittered glimpses across the different fixation points. So these, along with the data augmentation that we have, together they provide the right object-centric features required for robust recognition. So before we move on to the experiments, I want to quickly show the effects of object-centric data augmentation. So here we show the 2 different pipelines. One is for the standard model and the other is for a FocL supervised model. So for the standard model, the input is the entire image, whereas for FocL, it's the crop centered around the fixation point, the red fixation dot. Now, random resize crop is the first transformation that is applied to an image in a classification pipeline. So as you can see here, that ran the five, say if we train for 5 epochs, then the random resize crop at each epoch is visualized here. So for some epoch, as you can see for this case over here, you have the label of the foreground, but the features you're seeing is just water. Similarly, for this fish over here, you have a whole lot of features coming from the background, which results into spurious feature learning. Versus for FocL, what you can see is that all the different all the different uh, random resize crops are applied to the foveated glimpse, and these just show different glimpses of our foreground. And you have some very zoomed in version of the foreground and also some zoomed out version of the foreground. So basically, it gives you very good features that is required for robust learning. So next we look into the experiments. Let's look at the experimental setup. Now, if I claim that through foveated vision or through an algorithm like FocL, we want to show the benefits, and we show these benefits across 3 different verticals. First is the question of memorization. So we ask, does FocL reduce memorization? Now, to show this, we take help of cumulative sample loss, which is a proxy for measuring how hard it is to learn a sample, that is the difficulty of learning a sample, and we track the CSL profile of FocL and standard training. Then we probe feature stability across the training and validation sets via PGT L2 attack. Here our claim is not adversarial robustness as such, but we use adversarial attacks to test feature stability, and we link adversarial robustness to memorization here. And the third is a qualitative analysis of Feldman-Zhang's top 1% hard samples to show that how FocL reduces the CSL scores of all of these 1% of top hard samples. Now, if uh, one phase of a coin is memorization, the other phase is generalization. So the other question we ask is that, does FocL improve generalization? And we show this under foveated inputs. So we do in-domain performance, that is, we train on ImageNet and test on ImageNet. Then we do cross-domain generalization, that we trained on ImageNet v1 and we transferred those to ImageNet v2 and COCO, but in a zero-shot setup. So we don't fine-tune the models in any way. We just take the models and we infer them on these two unseen data sets. And to do that, we bring back our dorsal ventral structure back, what we proposed earlier, and we use SAM as our proposal network. And the final question that we ask is that if FocL reduced memorization, that means easiest learning, does that easier learning also improve sample efficiency given we have supervised bounding box provided? So our experiments will cover these three different vertical axes. So let's look at the experimental setup for the first set of experiments. We use ImageNet extensively for our experimentation. So for this analysis, we use ImageNet, and this is our 100K partition where we have 85,000 for training and 50,000 for validation. FocL is trained on bounding boxes, of course, with our FocL algorithm, and the standard model is trained in a standard supervised way. And for this experimental setup, we set k equal to 1 because we want to actually test how the algorithm works. And if we use multiple glimpses, then that might dilute the effect that we want to show that comes from foveated training for this setup. Later, we are going to show results with k equal to 3. And again, as mentioned earlier, these are the 3 kind of experiments that we're going to perform to show that does FocL reduce memorization or not. So first, let's see cumulative sample loss. This is a work published in ICML from our lab in the previous year. So what it says is that we calculate CSL via this equation, and it says that the loss calculated per epoch, when you sum across all the epochs, if the loss is high, then it says that the sample is harder to learn. If it's low, it says that the sample is easier to learn, and this has been shown as a good proxy for memorization. So the first result we show here is the histogram of CSL, focal versus standard. Standard is shown in red and focal is shown in green. Now, as we showed in our first slide, that with such training, which reduces the intra-sample uh, uh, differences and promotes feature learning between the right label and the right object, we see that a lot of samples from the tail in the original setting has been shifted to the mode with a higher mode over here, and the reduction in CSL loss has been shown here from 206 to 72 based on this data set and the classification network. Again, we don't claim that we remove tail altogether. Of course, there will be tail, but a lot of samples from the tail have been shifted to the mode. So that is one result that we show. The other is per sample loss and confidence trajectory. If you see here with the person feeding this llama and the label being llama, uh, the issue that we mentioned earlier, we can see this from the loss and confidence trajectory, as things are very jittered here, that it's a very hard sample to learn because of so many different factors, a lot of background coming in, and this is shown by the CSL value here. Versus for our foveated glimpse, where we remove the person altogether with the help of the bounding box, here both the loss and the confidence is more stable, and this also shows from reduced CSL value. So the CSL profile and one sample showing the trajectories of these metrics, we show how CSL can be used to really understand that how focal kind of learning benefits by lowering memorization. So more of such samples are provided in the appendix of the paper. So next we'll look into the Feldman-Zhang top 1% samples. That we take the top 1% memorized samples with the pre-computed Feldman-Zhang scores, and we intersect that with our partition A training set that gives us 820 samples. And we also perform a binomial test, which is a pair test to show that for each sample, the cumulative sample loss is lowered by focal than the standard one, and the details are provided in the appendix. So out of 820 samples, I think we see 819 samples showing this effect, showing that focal is also effective for the top 1% memorized samples. And these are some qualitative analysis that we show. A key feature is that a lot of these samples have background, which we try to remove because of our foveated learning. And this is a feature that we see. We don't make any claims regarding the foreground ratio or anything. It's just an observation that we make that a lot of these highly memorized samples have a lot of background features, which is one of the probable causes of shortcut learning, which FocL aims to remove. In this slide, we show adversarial robustness of FocL compared to the standard model, and this is one of the contributing tests to show that why FocL reduces memorization. So the attack here is a white box PGD L2 with random restarts, and these are the epsilon values across which we sweep. These graphs show that at each epsilon, at both the training and the validation sets, FocL has a superior robust accuracy than a standard model, hinting to feature stability against white box L2 attack. The other experiment that we perform is the mean adversarial distance, which is the smallest perturbation forcing a misclassification given by this equation. More details are in appendix, and we find out that FocL has a relative 62% requires a more 62% more adversarial budget for its classifications to get flipped into misclassifications. So the conjecture is that if your model is more difficult to flip, that tends to stable feature learning, which also shows that it has less connection to shortcut learning, where the learned features are brittle, and that is what we see in terms of the standard model. We link this to our first result that we showed, which is the CSL profile. So these three experiments together kind of hint that FocL reduces memorization. So next we are going to look into the generalization experiments. So before we move on to the generalization experiments, I want to quickly mention one note from the adversarial robustness experiments. Each model is attacked on its respective input. For example, standard model is attacked, the perturbation is applied on the whole image, whereas for FocL, the perturbation is applied only to the foveated crop. So the gain also kind of encapsulates the fact that um, uh, FocL has been attacked on the foreground itself, which might be a cleaner measurement of the label that it's asking to be flipped. Also, it's slightly a more difficult attack for the standard model because perturbations, as we know, can hide in the background as well. So just wanted to quickly mention that before we move on. So now we look into the generalization experimental setup, and for this we scale up to the entire image data set, which has all the bounding boxes. And out of 1.3 million samples, we only have a bounding box of 482K samples, and we perform our experiments on this. For testing, we again use the validation set, and we sample like 2K samples for our testing. Quickly mentioning, this 30K is again from the training set because we want the model, again, the bounding box crop for validation as well. So these are disjoint splits. These two splits are from the training set, and this is from the validation set. Uh, the models that we use in this setup, along with the standard ResNet, we use two different versions of FocL with k equal to 1 and 3. We have additional baselines here. One is a ROI align classifier, which essentially is the classifier of a two-stage faster RCNA network, and it's trained on feature pooling. Hard mask is another classifier, which is trained with the data set mean padding outside the bounding box at scale. So what we do is we use the entire image and we just mean pad outside the bounding box, and then we apply the augmentations. Now, since I mentioned that we are also going to show cross-domain generalization, here we use SAM as our dorsal network, and more details are provided in the paper as well as appendix. And the tests we do is first we do in-domain generalization, and then we try to transfer it to the other domains. In this slide, we show in-domain generalization, that is models trained on ImageNet v1 and tested on ImageNet v2 on 2K samples from the test set. So inference strategy says the exact way it was trained on, and so we maintain that during testing so that we do not incur any additional distribution shift. So from the results, we can see that FocL has a close to 7 to 11% top one improvement across the baselines, and we can also see from top 5 that there are significant improvements. One key thing to note is that between FocL single crop and multi-crop, there is a bit of difference, which shows the effect of the multiple glimpses that it learns, and the inductive bias that we wanted to put into this setup. Okay, this is in-domain generalization. And the next couple of slides, we show how this learned features are transferred to cross-domain data sets like ImageNet v2 and COCO. Before we get into the results, I want to quickly recap an active vision framework and how we use that for inference here. So you take the input, you pass through your proposal network, which proposes a bunch of bounding boxes on the image, depending on how many objects are there. Then we take these proposals and the input, and based on what inference strategy we have used for training, we use that and pass those proposals through the ventral network, and we use the any correct metric here. That means that if the model correctly predicts one correct prediction across all the proposals, we take it as a correct prediction. One important point why use SAM for this is that SAM is a foundational model which excels in zero-shot prediction. And since we try to have a fair transfer between our trained and cross-domain data sets, we wanted to use SAM because we don't have to perform any additional dataset specific fine-tuning. And what we want to show is that if you really learn the FocL way, that is the object-centric way, those features transfer better than other methods which also pick up dataset specific properties that hinders generalization. This is exactly shown in this table. As you can see, is that FocL also, in this case, on V1 along with SAM, uh, maintains its superior performance across all the baselines. ROI align really comes close here, but cuts the gap to 2%. But the thing is that the way it's trained is that it uses feature pooling across the entire image, after which the ROI align network is applied. So it also captures dataset specific properties that do not transfer as well as the object-centric properties that FocL learns. So from V1 to V2, we can see that FocL maintains a good amount of improvement than the other baselines. Next, we're going to see similar results on COCO. So here we are reintroducing the framework. We follow a similar pipeline, except the output is NMS filtered, and the bounding box with the topmost confidence prediction is classified as the correct one. Here we use mean average precision for our detection accuracy, and we use two different IU thresholds, and we limit the proposals to 20 and 300. 300 because for a DETR kind of a pipeline, you use close to 300 queries for an image. We just wanted to match that and see how it goes. From the results, you can see that for two different IU thresholds, SAM and FocL is still much better than SAM and standard. This shows that the object-centric features that FocL learns, it's better for ImageNet to COCO transfer as well. And we use only direct mapping. That means 65 out of 80 or 90 COCO labels are same as ImageNet. So only we use those kind of mapping. We do not use any super category mapping, and the details are presented in the paper, as well as a link to the GitHub repository, which we follow in order to make sure that the classes are properly mapped from ImageNet to COCO. Next, we are going to see some qualitative samples. In this slide, we see some qualitative samples. So on the left, you have on this side, you have like 20 proposals per image. On the right hand side, you have 300 proposals, and you can see that how much it can vary based on how many objects you have. One quick clean takeaway is that FocL predictions are more correct by standard than standard. And for example, here you can see that FocL has more correct predictions as indicated by the green boxes, whereas standard has one less number of correct prediction. Also, the predictions that they make, some are incorrect. So again, these are qualitative results which back the quantitative analysis we showed earlier. More samples and results are provided in the appendix. Here we come to the last question: does FocL improve sample efficiency? To show that, we bring back our 482K thousand data set, which has been used to train the standard model and FocL single crop multi-crop. We additionally include another baseline, which is a standard model trained on the entire image data set, 80% for training and 20% for validation. So here we show 4 different baselines, but the main comparison is between FocL single crop and the standard model, which sees more than twice the number of samples for training. What it shows is that even with more number of samples, it cannot match the top 1 and top 5 for a foveated method, which sees more correct features that are required for correct classification. And also the point that we are trying to make is that since FocL reduces memorization, that means it makes learning easier. That easier learning also has a positive effect of sample efficiency. Please note, we are not showing or making this method as a core set method. We are just showing the positive effects of foveated learning. We also show similar results on smaller splits, and that has been provided in the appendix. So concluding our slides on the presentation, we introduce FocL, a foveation-based object-centric training algorithm, where we can vary the number of glimpses for training. To show the benefits, we ask 3 different questions. The first one, we ask, does FocL reduce memorization? And we validate this through 3 different experiments. Next, we ask, does FocL improve generalization, which can be backed by in-domain and also cross-domain generalization, and also how we show how foveated object-centric features transfer well to even more complex cluttered datasets like COCO. And finally, we show that FocL's easier learning also has positive effects on sample efficiency. For more details, please look into the paper. The code has been also uploaded to GitHub. And thank you so much.